Okay, in this problem we're also going to use Icebox, but it's going to be a little bit different than the one we did in the first video. So first of all, I know that I'm going to use Icebox because our problem says if 0.3 moles of SO3 and NO were placed in a 1 liter flask and allowed to react, what would be the equilibrium concentration of each gas if Kc, which is the same thing as KEQ, equals 0.5? So I've been asked to find the equilibrium concentrations, and I haven't been given enough information to be able to find that by simply using my KEQ equals products over reactants. So I have to do Icebox. So first of all, as before, I noticed that I have 0.3 moles of each in a 1 liter flask. So I need to find my molarity, which is my molarity, remember, is moles over liters. But this is really easy because I just have 1 liter. So 0.3 divided by 1 is 0.3. So it makes finding my concentration values for SO3 and NO really easy. So to set up my icebox, I do my lines between each one of my compounds, and I do my I for initial concentration, change in concentration, and equilibrium concentration. And then I'm going to add the values that I have. So I have 0.3 moles per liter, so 0.3 molar SO3 and 0.3 molar NO. And I should mention it said what is the equilibrium concentration of each gas, and it doesn't tell us the phases, so we can actually assume in this case that each one of them are gases, that there are no solids or liquids. If there were any solids or liquids present, we could omit them from our icebox because their concentrations don't change, so they can be omitted from any KEQ calculations. So I haven't been told anything about the concentrations of NO2 or SO2, so I can assume that I don't have any to begin with. And other than my Kc, that's all the information that I've been given. So I'm still going to proceed with my icebox as usual and hope that I can eventually get to a point where I can figure out some numerical values for my equilibrium concentrations. So first of all, I can put in my plus and minuses. So I put my minuses in everywhere there is a number greater than 0 in my initial concentration because I know my reactants. I'm going to be using those as I create the products, so their concentrations are going to decrease. And wherever I have zeros, I can put pluses in my change row because I can't create negative amounts of something. So if I'm starting with nothing, I know my concentrations are going to increase as the reaction proceeds. Now I'm going to put an X everywhere there's a compound and bring up any coefficients that are there. And there are no coefficients, so in this case, all I have are X's in my change row. And I have no numerical values in my equilibrium concentration row, so I can't find out and solve for X at this point. I just have to kind of keep X in the box for right now. I can't substitute it, unfortunately, with any values because I haven't been given any equilibrium values from which to work. So I just do my I plus C equals E. So 0.3 plus minus X is just 0.3 minus X. Same thing over here, 0.3 minus X. This is X. 0 plus X is X. 0 plus X is X. Now I'm going to make this a little bit smaller so that we can continue to work and try to find some numerical values for our equilibrium concentrations. So I know that my KEQ or my KC equals the concentration of my reactants over, or I'm sorry, my concentration of my products over my reactants. So this is going to be NO2 times SO2 divided by SO3 times NO. And there's no coefficients, so I don't have to raise those to the power of anything. So now I'm going to kind of plug in, and I'm going to bring this up here so I can have a little bit more room to work. So I'm going to plug in the value that I know for KEQ, which is 0.5. And now I'm going to plug in each one of these values in my equilibrium row for each of my equilibrium concentration values down here. Okay, I'm going to erase some of this just to give us a little more room to work. Okay, so now KEQ 0.5 equals my NO2 is equal to X, and my SO2 is equal to X, so X times X, divided by my SO3 is equal to 0.3 minus X, and my NO is equal to 0.3 minus X. So I can actually simplify this to 0.5 equals X squared divided by 0.3 minus X squared. Now I want to simplify this even further so I can take the square root of both sides to get rid of these twos, my squares. So 0.5, so my 0.5 square root is 0.707 equals X divided by 0.3 minus X. Now it's just a matter of simple algebra. So I multiply both sides by 0.3 minus X. And don't forget to distribute. So you need to multiply the 0.7 times the 0.3 and by the negative X. So this is going to give me 0.212 minus 0.707x equals x. Now I continue by adding 0.707x to both sides, and I get 0.212 equals 1.707, because this one is essentially 1x. 1.707x, divide both sides by 1.707, and I'm going to get x equals 0.124. So that's my x value, but let's go back to our question and see what it asked. So it asked, what would the equilibrium concentration of each gas be if Kc equals 0.5? Well, x doesn't really help us. We need to plug this value back into our equilibrium row in order to have the equilibrium concentrations for each gas. So 0.3 minus x, so 0.3 minus 0.124 is going to give me an equilibrium concentration value for SO3 of 0.176. It's also going to give me the same thing for NO, 0.176. And then it's going to be, since x is x, I can just substitute it in. So my equilibrium concentration value for NO2 and SO2 is going to be 0.124 for both of these. So don't forget, once you've found x, to plug it back in to your equilibrium concentration row in order to find the equilibrium concentrations for each of your gases in your reaction.